Hey guys, Mr. Woods back here again just to do some more AP Chemistry. But hey, forget all that. Let's do the jokes, which is what I need and maybe you need. I know I do. Okay, I got two right there with those Mr. Wood classic stupid jokes. Okay, here we go. Why were the suspenders sent to jail? Because they held up a pair of trousers. And I don't know if you like that one. Here's another one. I think the second one's a little better. What's smaller than an ant's mouth? An ant's dinner. That would be true, right? Well, hey, first of all, I wanted to tell you guys a little bit. I can check on the YouTubes, and it seems like you guys are watching the videos, and hopefully they're helpful, and that's about all we can do right now, and we're just going to keep doing what we're doing. And you guys have chapter 15 quiz, and I'm going to make that due a week from tomorrow. Today's Thursday, so that is Friday. I think that's April 3rd, and I am going to send out to you guys. I'm not going to show you the work, but I'm going to give you the answers because I like you to, and then hopefully you guys can show your work and doing the answers. So today, and then we'll probably, I'm hoping we're gonna go for a little bit today, and then we'll go to finishing chapter 15, and then I want to just spend a couple days just on chapter 16 and 17, and I will send you a quiz for 16 and a quiz for 17. They're not as long. And just to make sure we kind of cover everything, and then I'm going to try and come up with maybe just some starting to practice and get ready for the AP test, and hopefully maybe that's about when we'll come back, and I don't know what's going to happen. But you guys are doing great. I'm missing you, and this is certainly not ideal situation at all. Okay, so where we left off was we did a titration problem where we took a weak acid, acetic acid, with a strong base, sodium hydroxide, and we went through the scenarios in the buffer region first, then at the equivalence point, and we saw, okay, here's the situation in this combination where at the equivalence point, where the moles of acid equal the moles of base, the pH wasn't 7. And then we did once we were past the equivalence point. Well, now I want to do a problem. I'm not going to spend a super amount of time, but we're going to do the titration of a weak base with a strong acid. So, and here is in the notes. And remember the note plate where you can find my notes is at mikeryan.altervista.org. And it's pretty close to the same notes that I'm giving. But anyways, here is where we are right now. So, the equivalence point is right there. I call it the inflection point. This time we're going from the upper left to the lower right. But kind of once the graph starts going down, once it turns over, that's the equivalence point. And we'll find the equivalence point in this problem. The buffer region is where it's flat here, and that's where it's got the components of a buffer, which in this case would be a weak base and its conjugate acid. And then where the pH changes dramatically, and that's where then the buffer has run out and the pH just drops dramatically. Okay, so kind of just looking at this in the opposite way. So here's going to be the problem we're going to deal with, and we're going to kind of go through all scenarios. So determine the pH when 25 mils of a 0.1 molar HCl is titrated with 10 mils of a 0.1 NH3 and 10 mils of a 0.10 molar NH3. So where I'm going to start this problem is, again, I'm going to write the equation. And I'm going to write this out with the HCl. But again, I'm going to ignore the Cl, like we ignored the Na before. So if I have HCl, because it's a strong acid, it's going to dissociate like that. And if I have the moles, again, if I get this into moles, I have 0.0025 and 0 and 0, and because it's a strong acid, it's completely gone. And then I would have 0.0025 moles of H plus and 0.0025 moles of Cl. And the Cl though, and the reason I did that, I'm not going to write that over and over and over again, is because the Cl isn't going to be a factor in the overall reaction. What's going to be a factor is the H plus. So this is what's technically really reacting here, is we've got the ammonia, and we have the H plus from the HCl, and it's making ammonium ions. So what we have here is this is the base, and this is its conjugate acid. Okay, and if I go back, and again, I'm doing an ice table, getting everything into moles. So I started here with 0.0010, and then the HCl, I had 0.0025, and then 0. So here again, ice tables. So initial, and then change. The NH3 is going to run out first. It's limiting. Okay, and then I'm going to have excess HCl. Okay, so there's my completed ice table. And the one thing I told you in these titration buffer problems, if we're trying to find the pH, if we have excess H plus or H3O positive hydronium or OH, I don't need to use the Henderson-Hasselbalch equation or anything else. And that's what happens here. I have H positive left over. And so because of that, and again, just like I was talking about in the last video, where I always mess up is I forget the denominator and to include the volume. And I don't want to do that. That would be a mistake. So this is the moles of H plus, and the volume, it was 25 mils and 10 mils. So it's 0.035. Okay, so so this is the concentration of the HCl. And yeah, there's conjugate acid left over, but because it's a weak acid, it's not going to produce nearly as much H plus, and so we can ignore that. So I have 0.043. So then my pH, just the negative log of that, gives me 1.37. Okay, so in scenario A, in this titration, 1.37. Okay, so now I go on to the second scenario. So now I go here, and one thing I needed to tell you and I didn't hear is the K for the ammonia, the KB is 1.8 times 10 to the negative fifth. You have to be given that to do this. So now we're going to reach B. We are now at the equivalence point, okay? Which means the moles of acid equal the moles of base. So I'm going to erase this. Again, I'm still going to have the same amount of H plus that I had before. So I've got NH3 plus H plus. So again, here's my reaction. This is what's going on. To write that out. And this time I have, remember the equivalence point is when we have equal number of moles of acid and base. Okay, so here, this time they both run out at the same time. And to me, just like I said in the problem that we did a couple days ago, this scenario, the equivalence point, to me is kind of the top of the hill in terms of the difficulty of this problem. At this point, because, again, here's our base, and here's the conjugate acid, but because this is a conjugate acid of a weak base, it is a strong enough conjugate acid to hydrolyze water. And only at the equivalence point do we now have to go one more step. And so now I'm going to go back to the NH4, the ammonium, and because it is a conjugate acid that is strong enough to hydrolyze water, I go another reaction. And I did the same thing in the scenario with the weak acid and the strong base. So I start with the 0.0025. This, the water I'm not concerned about. This X, which I'm going to ignore. Okay, and then I have X and I have X. So here, and again, I would have told you the KB. The KB is 1.8 times 10 to the negative fifth for the ammonia. Okay, and I would have to give, you'd have to be given that in this problem. There's no way you could do it without that. So I want to solve, because this is now acting as an acid, so I'm going to do the Kw, 1 times 10 to the negative 14th, over the Kb. Okay, and then I'm going to have x times x, or x squared. And again, I've got to remember the volume. So in this case, it's going to be 0.0025. Those moles, again, I'm ignoring that x, over 0.050. Okay, and when I've solved for x, what I will have solved for then is hydronium ion. And when I do that, what I get for hydronium ion is 5.27 times 10 to the negative 6. And now I know the H3O, and if I know the H3O, then I can find the pH. So if I do the negative log of this, what I get, the pH, it comes out to be 5.28. And again, this is the scenario talked about in the last video where we're at the equivalence point, but the pH is not 7. And then go back and ask ourselves, does it make sense if we have a strong acid and a weak base to have a pH less than 7? And that does make sense. Okay, so there's scenario 2. So that is at the equivalence point. Okay, and then the final scenario, C, and there I finally did include the Kb value, but now C, now we're going to have excess NH3. So again, if you got that, or you can go back and look at that. So now I'm going to do scenario C here. So again, I'm going to do the same thing. I'm going to write the equation. So I've got ammonia plus the H plus from the HCl, making ammonium ion. Okay, and this time in my ice table, I have 0.0035. So this time I have excess ammonia, 0.0025, and 0. So this is limiting. So this time the H is gone. And so what I have here is 0.0010, and then plus 0.0025. And now at this point, I said if you had excess H plus or OH, then you could find the pH from there. In this scenario, this is the best way, because here I have the base and the conjugate acid. The best thing to do to me to solve for pH is to use the Henderson-Hasselbalch equation. Okay. But again, you're given the Kb. The Kb is 1.8 times 10 to the negative fifth. And in the Henderson-Hasselbalch equation, this is the Ka. So this needs to be P, means negative log. And then I'm going to get to the Ka. So there's Kw, and then there's Kb, plus the log. And the NH3 is the base, so it's 0.0010. And the NH4 is the acid. Now again, like I've been saying a number of times, it's because I've screwed it up so many times myself, I really should divide both by the volume, but in this case, because that's going to be in both the numerator and the denominator, they're all going to cancel out. And so what I end up getting here is 8.86. Okay, so that is scenario there. So, and to me, these problems they're kind of hard, but I think they are hard. But when you do them, they're kind of cool when you can see how everything fits together and everything works together. Okay, so back to the notes. So we've done buffers and titrations. I wanted to go through a couple things and then introduce kind of the last point in the chapter, which I think is a possibility for the AP test. So I want to spend a little bit of time on that. I'm just going to skip this problem. This is one I'm not going to worry about. I did want to just briefly talk about this. If you remember in chapter 14, polyprotic acid is an acid that produces 2 or 3 H's. And you can tell from a titration curve, equivalence point 1, 2, 3, that this must have 3 ionizable hydrogens. And so, again, kind of goes back to polyprotic acids, which we talked about in chapter 14. And I did want to talk briefly about this page too. The lab that, and I don't know if we're going to have time, I have one lab I really like to do in chapter 15 on the acidity of some different beverages. But, and it also, it went into a little bit about how some indicators work. But the key thing is right here. I want us to note, which it says right here, is it possible for the pH of the endpoint to be different than the pH of the equivalence point? And just making the point, the endpoint is technically when the color in the indicator changes, where the equivalence point is where the moles of acid equal the moles of base. So is it possible for the pH of the endpoint, the color change, to be different than the pH of the equivalence point? That is a possibility. In designing an experiment, a chemist he or she wants to design the experiment where those are going to occur at the same point. And this is why phenolphthalein is such a good indicator. This shows this. This is what shows how phenolphthalein, usually in those titration curves where phenolphthalein changes, usually works for all where there's a big jump. And you can see phenolphthalein there in the indicator. And you can see where it's key that the indicator changes is somewhere where all of a sudden it jumps. And you can see here's stronger acids, and then the acids get weaker, and you can see here. But again, phenolphthalein usually falls right in there, and that's why phenolphthalein is such a good indicator. Okay, and I'm going to skip this page too. Again, this is something that's not going to be on the AP test, but it goes right along with what we're taught, what we've been learning about, is indicators themselves are weak acids. Phenolphthalein is an example. Like there's the structure of phenolphthalein. It kind of goes back to the pH equals pKa plus or minus 1. But, okay, I did want to do a couple problems on this page, and then we're going to stop. So let me put this whole page up. This is, if you remember what chapter 15 is about, is a combination of chapter 13, Equilibrium, and the double arrow going left to right or right to left, as well as chapter 14, which was on acids and bases. And we've really spent a lot of time, or some time, we could have spent more, on the chapter, kind of the 14 thing with titrations and buffers. This is something I think is a possibility to be on the AP test. So I want to introduce this to you today, and then I'll come back on Monday and we're going to do some more problems. And these are some pretty good problems, but solubility equilibrium. So we're talking about ionic solids and their solubility. And solubility is a measure of the maximum number of moles of solute that will dissolve in a solvent. And we're talking about an ionic compound. And so what we do here is we just show the ionic compound dissociating in water, and we write out K, just like we did in chapter 13. But always on the left in these KSP problems, it's a solid. And remember, solids, we don't include those. Solids and liquids, we said they had an unchanging concentration, so it's just the 2 ions on the right. This is now called KSP, which is the same thing as KC, KP, KW, KA, Kb, it's the same thing. What's on the right on the top, what's on the left is again a solid. It's called the solubility product constant. Equilibrium means it's saturated. It cannot dissolve anymore. Problem, write a dissociation equation and expression for Ag2CrO4. So this kind of goes back to some review that we did back in the fall and even back in first semester or in first year. And KSP problems are something that we did touch on in first year chem. So this is at this point is definitely a little bit of review. So the first thing I'm going to do here, it says to write a dissociation equation in the KSP expression. So before we do any numbers, we're just going to write out what is going on here. So we've got Ag2 CrO4. And if you can name this, this is what it's going to dissociate into, silver chromate, and that's what it's going to dissociate into. So it's going to dissociate into silver, and this would be aqueous, and then chromate, and then always what was tricky, and hopefully for you guys, you're good on this, but when you first learned it, it's always tricky about these subscripts. And remember, if a subscript is part of a polyatomic ion, and now as we're getting closer to the AP test, I would occasionally do some review of the polyatomic ions, but this 4 is part of chromate. And when a subscript is part of a polyatomic ion, it's going to stay as a subscript. But this 2 is there because chromate was a -2 charge. And so when a subscript is not part of a polyatomic ion, it then goes to the front and becomes a coefficient. And then the KSP expression would just be Ag squared times CrO4. And again, this is really the same thing with the Kc that we were doing back a month ago in chapter 13. So there is the dissociation equation, and there is the KSP expression, and again, because this is a solid, I don't include it. Okay, so next problem. Let me just do 2 more, almost done, and then I'll come back on Monday. Okay, so now, it says general types of solubility problems that are easily confused. Given the solubility, determine the KSP. So the solubility of silver sulfate, determine the KSP. So here we're given the solubility. So in these problems, to me, we're always going to have to, first of all, do what I did here. We're going to have to write out the equation for the dissociation. So here, the silver sulfate is going to dissociate into silver and into sulfate. And in these KSP problems, it's always 1 solid on the left and 2 aqueous ions on the right. And again, this 2, because it's not part of a polyatomic ion, it became a coefficient, but this 4, because it's part of sulfate, stayed as a 4. So then if I write out the KSP expression, I'm going to have Ag squared times SO4 to the 2. Now in this problem, we have been given the solubility of the silver sulfate. So again, I'm going to go back, and you guys, I'm sure, hate ice tables now, but just to be consistent. So I'm told that I have 0.015 moles of this. Well, what that means is that this is completely gone. And over here, because it's a 1-to-2 ratio, it's going to make twice as much. So I just took 0.015 times 2. And then here, because it's 1-to-1, this would be 0.015. Okay, so I just used an ice table, and now I'm going to plug in the numbers. So the silver is 0.030, and then I got to remember to square it. This is equilibrium. And then I have 0.015. Okay, so let me do this. 0.03 squared times 0.015 gives me to 2 sig figs 1.4 times 10 to the negative fifth. And again, the K value is one of the rare numbers that we have that does not have a unit on it, okay? Okay, so that's the first kind of KSP problem, is we are given the solubility, find the KSP. The other kind of problem is this one, given the KSP, determine the solubility, okay? So I know this is turning into be quite a set of problems, but let's do this one, and then we'll call it a day. Okay, so hopefully you guys can see that. Okay, so I'm going to do the same thing. So okay, in terms of the first step is I'm going to write out the dissociation equation. Okay, so what I got here is copper to iodate. So again, you got to review on how you write this. Copper 2, and then iodate, like chlorate, is ClO3 negative 1. Well, iodate is IO3 negative 1. And so the formula for this would be like that. Okay, and it would dissociate like this. So again, I'm writing out the just the dissociation equation, and then the KSP equation is copper times iodate, and that would be squared. Now this time we are told the KSP value. We're told in the last one we did, we solved for KSP. Here we're given the KSP. It's 1.4 times 10 to the negative 7th, and we're trying to figure out the solubility X. So again, if I go back to ice table, it's like this. But this time, I don't know the solubility. I'm trying to find that. So minus X, 1 to 1, so this would be plus X, and 1 to 2, so this would be 2X. Okay, and now I'm going to go back down to the KSP equation. So I have X, and then I have 2X squared. So X here, and then 2X there, and then squared. And so what I end up with then is 4X cubed equals 1.4 times 10 to the negative 7. Okay, what I end up solving for X, the solubility, comes out to be 3.3 times 10 to the negative third. Make sure of that. So I got 1.4 times 10 to the negative 7th divided by 4. Yep. And then it's said to solve for the iodate concentration. Well, iodate is 2X. So iodate is equal to 2X. So just be 2 times 3.3 times 10 to the negative third equals 6.6 times 10 to the negative third. Now this has a unit on it. This would be molarity or moles per liter. The first one was KSP. This one was solubility, which is a unit just like molarity. So I do think there's a chance that KSP problems are going to be on the AP test, and so I kind of got into them today. I'm just going to put up the next one and something you guys can look at, and this is where we're going to start. And I'll come back on Monday, and like I said, you guys, from what I can tell, are doing a good job and trying to at least follow along on the YouTube videos, and hopefully that's helpful. And to keep trying those problems. If you have any questions, email me. I'm checking my emails periodically throughout the day. So keep up the good work, and I'll talk to you the next time I'm going to make a video will be on Monday. Have a good weekend. Bye.